I've been talking at NICE for the last couple of years, and Murat has been graceful to let me give some updates of our work. So our work focuses mostly on exploiting emerging technologies like memristors in designing neuromorphic systems. So in today's talk, I'm going to talk mostly about how we use these memristive devices to scale up and build large-scale architectures, particularly for spatio-temporal processing applications. A quick overview of neuromemristive systems. I think earlier talk by Tarek covered a lot about the devices and the circuits. So I just wanted to give a quick high-level motivation on how we are approaching in designing these systems. We try to take inspiration from the brain, and build adaptive computing platforms. And particularly the memristor devices are used to facilitate efficient computation and learning. The end goal is to have basically efficient natural processing tasks that are run on hardware platforms. So the focus of today's talk is on two specific architectures. First, I'll talk about the reservoir architecture that we've been working on, both on a commodity FPGA and a neuromemristive system. And the second is the HTM architecture, which was built using a neuromemristive system and a commodity flash. Most of you probably already know about reservoir architectures here. I think Dr. Maas just left, but Wolfgang Maas and Jaeger are pioneers in designing this reservoir computing framework. It is very efficient recurrent network topology, particularly because the training process is very simple and it is very efficient to realize in hardware. In our earlier work, we looked at different topologies on how to realize this reservoir. So we looked at the basic ring topology, which is easy to realize in hardware. It has fewer number of synapses, and as you can see, the node-to-node connections is very simple, but it also has very slow response, so it has high delay. Then we have been looking at other topologies which have center nodes and other hybrid topologies, but where the diameter is low and the average distance is low. But there was a specific topology that directly maps the reservoir onto the hardware, and that's where we've started looking at the twisted toroidal network, where the reservoir can be exactly mapped onto this toroidal structure. And there is a lot of color coding here, but you can see that from the input to the reservoir nodes, we have a specific set of the toroidal connections, and between the reservoir nodes, we have a different set of connections and so forth. And within each of these nodes is what you can see is the reservoir neuron, and you have those synapses that are connected to the different, to the other nodes or adjacent nodes. These are all implemented using memristors. So before we implemented this using a neuromemristive system, we first implemented it on two reconfigurable platforms, FPGA Vertex 5 and Vertex 6. If you ask me why we implemented on those, because those were the platforms that were available for our lab at that time. But we are exploring other platforms right now. And we did analysis. This is like a simple neuronal design in the digital framework, but we just kind of compared the power consumption or utilization of the power on these different platforms. And it is very much guided by what the actual baseline platform is, as you can guess, because there is a lot of additional overhead on these systems that is really not required for these architectures. Then we looked at the reservoir or the neuromemristive system for the reservoir. So before we actually implemented this, we took a step back and said, well, we've been looking at synapses and neuron designs using memristors for a while, but one of the things you could take advantage in a reservoir is that it has random initial weights that are distributed to the reservoir. So if there is a way we could use the process variations within the hardware to kind of generate those random weights, then we could save significant hardware overhead in designing the system. So we kind of designed a synapse utilizing process variations, and based off of that, we actually built a simple crossbar structure with the reservoir outputs. And then we did the circuit analysis, the Monte Carlo analysis of how these random weight distributions are. You could see that how the random weights are distributed and how the random biases are associated within the synapse. And then we also compared what would be the advantage of using our proposed synapse over a baseline synapse, particularly in terms of area, because in the end we are trying to have an area and energy efficient system, You could see that on the x-axis here for all these different realizations, so for all those different distributions, you could see how the area of the proposed synapse is pretty uniform in there. But you could see as if you require a lower weight resolution, then a baseline synapse is better than using this proposed design. So we compared this with different data sets with EEG and EMG. I'm just showing the EMG data set results here. So we had about 84% classification accuracy. Here we are actually trying to look at the 5 fingers movement, and we were able to get a pretty good classification accuracy, similar, comparable to other techniques that were used within this data set. And we also did the power consumption analysis. On the left is how we estimated the power for each of the individual components, and for the whole architecture, we kind of looked at as the reservoir size is varying, how the power dissipation is changing, and for what specific topology we have a lower power. So the one-way ring topology obviously has lower power consumption compared to others. And the random obviously has the highest power consumption. And right now we are looking at optimizing this and extending it into liquid state machines. So the next part of the talk is going to show some of the work we have been doing on the hierarchical temporal memory architectures. So before we design an architecture or any hardware for this, it was really hard to understand or how to design this in hardware. I wish Jeff was here to listen to this, but actually their team was very helpful in making us understand this. So the first step for us was to have, like a typical hardware engineer, we wanted to have like some kind of formalization for this design. So the first step we did was to actually formalize the spatial pooler. And this paper was recently published on arXiv if anybody is interested, and all the code is also open sourced out. For those of you who are familiar with the HTM, there is spatial pooling and the temporal pooling components within the HTM. So we started just first exploring the initial part, which is the spatial pooling, and we were able to formalize it. So the goal of this work was to explore what is the primary learning mechanism within the spatial pooler. So we kind of identified 2 distinct components, basically permanence selection and the degree of the permanence update. And we use like a maximum likelihood estimator for determining the degree of permanence update. I don't want to go through all the math for this, but I'll be happy to discuss with you offline about this formalization. And then we were testing this initial tests were with very simple test cases like handwritten digit learning, whether it's able to recognize the digits accurately. And then we also did a simple analysis with predicting the alphabet. Given A, was it able to predict B? I mean, whether it's able to predict the sequence efficiently. So it was working pretty well in that context for both of those. And then, so we've taken 2 approaches in building just the spatial pooler component. So the first part was to build it using a neuromemorystive system. The figures are a little blurry, I apologize for that. On the top left is what we show, like how we are doing the different phases within the spatial pooler, like the overlap and the inhibition phase. And the inhibition phase itself, we used a winner-take-all circuit, and the memorystive synapse, the neuromemorystive designs are used in this overlap phase. And we tested this with, again, early test results using AR phase data set for basically sample face recognition problem using different conditions like emotions, light conditions, and occlusions wearing glasses or scarves. So depending on some of the complexities, you could see there is a deterioration in the accuracy, but overall I think it was in an 81%. So this data set has 100 classes and 2,600 facial images, if any of you are interested. So the second approach was, okay, we are looking at this neuromemorystive systems, but this is a long-term trajectory. Is there a way we could use existing or commodity systems to kind of design these architectures? So we were looking at, in collaboration, we were looking at particularly storage processing units, because these have been modeled like to have 100 times lower power consumption and compared to CPUs or GPUs for a wide range of applications. And these systems are there already. So what we did was we built off of this system using to implement basically a flash-based architecture. The details of this work will be published within a month, but this is like a high-level bird's eye view of what we're trying to do. You could see the model we are integrating is very minimally invasive. So my student named it gray matter flash. I don't know if it is an appropriate name, but just to say that's the model that will be integrated within the system. Basically, so these devices can exploit existing interfaces within hyperscale data centers, and we did some analysis of the spatial pooler, how the different parameters within this are stabilized or affected. So for example, on the left is the boosting. How is the boosting stability based on the size of the network and how much time it takes to actually simulate the overall network. And we were able to, we just got, this is like fresh results, like my student just sent these to me a couple of days back, but we got like 99% accuracy for simple MNIST classification, and we are just getting the power results for this. So I would like to thank all my students who have been working hard in getting these large-scale designs, and thank my collaborators for helping us doing some exciting work. Thank you.
Thank you. So this SSD implementation, is this on a real piece of hardware, or is it a simulation?
So right now, so we started off with transaction level modeling, and then we did RTL, VHDL modeling, so, and synthesis. So it's not actually put on a system yet.
Are you planning to do so?
Yes.
Okay. Other questions? Yes.
I have two questions concerning your liquid state machine implementation. So first of all, you mentioned that you'd like to have some diversity in your liquid, for which I believe that memristors are pretty good. The question is, how did you do the training of the weights from the liquid to the readout with memristors?
I just wanted to clarify, the reservoir itself does not use memristor synapses. So the synapses we use with the memristors are at the output training node, and it is, depending on the class of applications we use, linear regression. And the randomness for the weights were generated from the CMOS circuit that we have showed there. The process variations within that circuit were exploited to generate those random weights.
I see, thanks. And the second question would be, what would be your opinion on how this approach, the LSM approach, scales to more complex problems? At
the architecture level, the doubly twisted toroidal architecture, I think that was shown by several other research groups also over the last couple of days. It's a pretty scalable model. But I think for more complex systems, there has to be slight variations of it to kind of scale to those systems.